Your logs show HTTP 200 from Twilio, but users aren't getting OTPs. The notification service retried every 2 seconds, triggering a soft ban that made all subsequent sends silently fail. Here's exactly why. Welcome to TheCodeForge. Before we dig into that production issue, let's cover design a notification system. A notification system delivers messages across push, SMS, email, and in-app channels. It decouples event producers from delivery, using queues for backpressure and a state machine to track every message from created to delivered or failed. Define SLAs per notification type. Critical OTPs need under 1 second latency. Promotional emails can wait. Route critical messages to a dedicated high-priority queue to avoid starvation. For 10 million daily active users, estimate 50 million notifications per day. Peak QPS can hit 2,300 for critical events. Storage grows to 40 GB per day plan for hot-cold tiering. This Python snippet calculates daily storage. For 50 million events, event metadata takes 25 GB, delivery receipts add 14.5 GB. Use these numbers to size your database. The architecture has 4 layers: ingestion via Kafka, processing that enriches and fans out, delivery workers that call providers, and tracking that captures receipts. This decouples producers from delivery. This Java record defines a notification event. It includes an event ID, user ID, type, channel, template, and payload. Validation ensures required fields are present. 2 core tables. Notification event stores the original event, delivery receipts records each attempt. Partition by time and index on evented for fast lookups. This SQL creates the 2 tables with partitioning by created at. Indexes on evented and userids speed up queries. Partition monthly to keep each partition manageable. Fanout converts one event into many deliveries. Direct fanout does per-user lookups for low latency. Batch fanout groups users by segment for high throughput. Use tiered routing. Critical events go direct, bulk go batch. This Java service implements tiered fanout. Critical events use direct fanout for speed. Bulk events use batch fanout to reduce database load. Third-party providers fail. Use exponential backoff with jitter, 1s, 4s, 16s, 64s. After max retries, move to a dead letter queue. Idempotency keys prevent duplicate sends. This Java retry service uses exponential backoff with jitter. After 4 attempts, it moves the task to a dead letter queue. The jitter prevents thundering herd. Rate limiting is per user per channel per day. Check preferences before sending to avoid wasted compute. Cache preferences in Retries with a 5-minute TTL. This Python code implements per user per channel rate limiting using Retries. It also checks user preferences before sending. Rate-limited messages go to a dead letter queue. A validator checks required fields and rejects malformed messages. A prioritizer tags each message as P0, P1, or P2. P0 messages go to a dedicated high-priority queue. This Python code validates incoming notifications and tags priority. P0 messages like OTPs get immediate attention. P2 promos can wait. A pipeline decomposes processing into ordered stages. Each stage runs independently and fails without losing the message. Dead letter queues catch only the errored stage. This Python code shows a simple pipeline with 2 stages, template and send. Each stage has its own input queue and runs independently. The scheduler sits before processing pipelines. It delays messages based on user timezone, batches to respect API limits, and prioritizes by event priority. This Python code schedules events based on user timezone. Events for users in New York are delayed by 1 hour to avoid sending during quiet hours. This is the same issue we highlighted at the start. Here's exactly why that happened. Users reported missing OTPs, but logs showed HTTP 200 from Twilio. The carrier had soft banned the account due to rate limits, silently dropping messages. Aggressive retries every 2 seconds made the problem worse. The fix was to implement a sliding window rate limiter per provider, reduce retries to 3 with exponential backoff, and add delivery receipt callbacks. Now, if a carrier soft bans, the rate limiter prevents further sends and the callback alerts the team. This is the exact mistake from the incident. HTTP 200 from Twilio does not mean the SMS was delivered. Always monitor delivery receipts and compare sent vs delivered counts. A developer set max retries to 10 with a 1-second delay. During a provider outage, millions of retries saturated the worker pool, blocking new notifications. Always cap retries and use exponential backoff. One team stored all notifications in a single Kafka topic. A spike in bulk email lagged OTP processing by 12 minutes. Use separate topics for critical and bulk traffic. Never hardcode stage order. Use a config YAML to define the pipeline DAG. Otherwise, adding a stage like content filtering forces a full redeploy. Scheduler offsets are additive. If you delay by timezone and by channel backpressure, events pile up. Cap total delay to 24 hours max. The article emphasizes monitoring delivery receipts, but note that some providers, e.g., Twilio, only send status callbacks if you explicitly configure a status callback URL in your account dashboard. Without that configuration, you will never receive delivery receipts, making silent failures invisible. Always verify that your provider account has webhook endpoints set for all channels. The article mentions synthetic probes for detecting channel failures. Here is a concrete implementation. A cron job that sends a test notification to a dedicated test device or email address and verifies delivery within a timeout. If the probe fails, trigger an alert. The article recommends storing idempotency keys in Retries with a TTL longer than the retry window. However, if your retry window is, say, 5 minutes, but the upstream producer might retry the same event hours later, e.g., due to a delayed webhook, you risk duplicates. Set the TTL to at least 24 hours or use a persistent store with a longer retention to cover delayed retries. To debug notification issues, first check delivery receipts via provider callbacks. For delays, inspect Kafka consumer lag. For duplicates, verify idempotency keys in Retries. Test channels manually with curl. Let's run through some common interview questions. Design for 10 MDAU. Use Kafka, tiered fanout, per channel rate limiting idempotency keys. Handle duplicate notifications. Did up with user id plus type plus event id in Retries, suppression window, retry window. Email provider 500 error. Classify transient versus permanent. Exponential backoff. DLQ after 3 retries. And a few frequently asked questions. What is a notification system? A smart switchboard that routes events to channels asynchronously. Why use a message broker? Decouples producers from delivery, handles spikes, allows replay. How to respect user preferences. Store in DB, cache in Retries, check before sending. Key takeaways. A notification system decouples event producers from delivery channels. Isolate critical and bulk notifications into separate queues. Rate limiting must be per channel and per provider. Always monitor delivery receipts and use synthetic probes. Ready to go deeper? Up next, design a search autocomplete, then design a payment system, then design a live video streaming system. Find them all at TheCodeForge.io. Thanks for watching. The full article and code examples are covered in detail at TheCodeForge.io.